Hello and welcome back. So in the last lecture we looked at finite differences and finite volumes. So now we are prepared to look at finite elements. So let's recap a bit. So in finite elements we are discretizing the domain into elements, and then we are constructing an approximation using a piecewise continuous polynomial approximation. So the way to do this is we take these piecewise polynomials and we interpolate them. Okay, and this approximation has to be then formulated into an actual system of equations. So for this we use what is called as the variational formulation. So 4 steps. So first, represent the solution in interpolated form, then use the variational statement to convert it into a system of equations. So these are integral equations, so you have to numerically integrate them, assemble them into the matrix, and then you just use your linear algebra to solve it. Okay, so in this lecture we are only going to look at the first part, that is the interpolation. So this part, the second part, is a bit more elaborate, so we'll look at it in the next lecture. So let's start off by a comparison with finite volumes. So let's recall that in finite volumes we talked about piecewise constant solution approximation. So we considered the cell average value, we placed it at the cell center, and then we just said that the same average value just holds over the entire cell. Okay, so if the average value inside this cell was 1 and this cell was 0.5, so what really happens at the boundary? What happens at x3? Okay, so at the boundary we neither have 1 nor 0.5, we have a jump, we have a discontinuity. Okay, so the difference here in finite elements is that in most of the cases, so you might have heard about, for example, a Navier-Stokes formulation in which the pressure is modeled as by using piecewise constants. So it's possible, but in most of the cases we are taking a piecewise continuous representation. So what is this representation? So here we place nodes at the edges. Okay, right, and then we connect these nodes to polynomials. So let's look at the next slide. So we place nodes at these 2 edges, right? So if we are considering this blue element, so let's place nodes at these edges, and then we connect these nodes by continuous polynomials. Okay, so if I would shift this node up, if I would increase the u value, these polynomials would also shift. Okay, and so the value inside this element, the value of the solution inside this element, the approximated solution I should say, is actually scaled, right? Because what is done is this line, this orange line, which is the solution, we are trying to interpolate it using these 2 lines. Okay, so if this node goes up, this interpolated line will also change. So let's look at the next slide, where this will become a bit more clear. So here we have a diffusion reaction problem where this red line is representing the solution, right? So let's get out of the slideshow mode, and this will make it more clear. So this is my coefficient, which is scaling these polynomials, right? So as I move this, these polynomials are also getting scaled, right? So in the finite element formulation, I'm asking a question that what are these coefficients? Okay, I have to find out. These coefficients are the undetermined variables. Okay, so here these are boundary points, so I know these 2 points. I don't know u here. Okay, so as I scale these nodes, the solution, which is this straight line, will also get scaled. Okay. More precisely, I should say that the solution is the integral under this straight line. Okay, so so the error here is really the error under the integral. The integral under this red curve, this red curve, minus the integral under the trapezius. Okay, so this black part here is the error. Okay, so this is basically the geometric intuition behind what we are trying to do in finite elements. So let's get back into the slideshow mode. Alright, so now let's look a bit more detail at interpolation. Okay, so interpolation is pretty common. So whether we were using log tables, sine tables, cosine tables, we have always been using it, but now we are interested in interpolation, which is piecewise continuous. Okay, so one way of doing this in a very simple way is using Lagrange interpolation polynomials. So in Lagrange interpolation polynomials, we have a certain property which is called as the partition of unity property. Okay, so this means that if I have defined Lagrange interpolation polynomials inside the domain, okay, So and so at every point inside the domain, if I sum these polynomials, the summation will always be 1. Okay, so here I have described the simplest form of Lagrange interpolation polynomials, which are linear Lagrange polynomials. The way to define this is that you set one of these nodes to 1 and the other node is set to 0. Okay, so you anchor one of these nodes to 0 and you allow the other node to move freely along with this coefficient. Okay, so here you can see x, this so we have this domain running from 0 to 1. So x is 0 at x is equal to 0 and x is equal to 1 at x is equal to 1, right? So basically pretty simple. So in 1 minus x, when I put x is equal to 0, I get 1, and when I put x is equal to 1, I get 0. Okay, so I'm recovering this partition of unity, and now I would scale 1 minus x and x with the respective coefficients, and once I do that, I'll get an equation of a line, and that equation is this one. Okay, so this is basically a linear interpolation. I could also construct a quadratic interpolation. So the idea is similar. Anchor two. So if we take this white polynomial, we are anchoring 2 points at 0, and we are allowing this point to move. Okay, we are setting it to 1 and multiplying it by the coefficient. Okay, so we do something similar with these red and yellow ones as well, and we could do this nice quadratic interpolation which can fit a parabola as well as a straight line. Okay, if you think of it inside the entire domain, you could think of these kind of functions. Okay, so you could just follow this line. This is piecewise continuous, right? So since these look like hats, we call them as linear hats. So typically they have a certain shape, and this shape can be thought of as 1 minus x and x. Okay, so that's the defining shape. One of the key properties is that this can interpolate not just the the unknowns u, but they can also model the knowns. Why? Because the knowns can also be thought of as a straight line. So the x coordinate can also be thought of as a straight line, right? So it's pretty obvious that you can interpolate that as well. So how would we go ahead and represent a differential equation? How would we represent du by dx? So in finite differences, we represent it like this, the forward difference. So in finite elements, we have written u as a combination of linear polynomials, right? So we would just apply d by dx onto this equation of a line. Okay, so here I have done something. So here I have done a change of variables. So I have changed the variable from x to x minus 2. Okay, why I have done that? So basically the domain is running from 2 to 3. So this line is x minus 2 and this line is 1 minus into bracket x minus 2. Okay, so since we said that linear hats are having this kind of a shape, right? 1 minus x and x. So it's good to represent it as that kind of shape. Okay, so we are just trying to represent this as 1 minus x and x. Carrying this idea ahead, we have what is called as a mapping. Okay, so to make coding really easy and also really like even to deal with curved geometries, unstructured grids well. So we have this concept called as mapping, where we model the physical element to a master element. Okay, so if the physical element is running from 5 to 6, so we can say that x minus 5, so this is x minus 5 and 1 minus x minus 5, right? So I just make this coordinate transform, that psi is equal to x minus 5. So as psi goes from 0 to 1, I will just recover this. So you can also make a coordinate, you can also consider a master element from minus 1 to 1 or 0 to 1. So I am using 0 to 1 here. Those two are the most commonly used. So let's look at a 2D kind of case, a 2D wire. Okay, so here you have this straight line. So you could map this physical space to a master space, right? Pretty straightforward. But if this line can be parameterized perfectly, okay, so let's say if this can fit a unit circle, so I could write down something like y like you must have heard about the coordinate system, like x is equal to radius into cos theta and y is equal to radius into sin theta. So if this is a unit circle, I can write this kind of a representation. So like when psi goes from 0 to 1, it will just trace this curve, and then I can also capture the variation inside this really well. Okay, I could integrate inside this. So this is really the power of finite elements, and we have kept the solution continuous here, so there is no issue. Okay, so this shows the strength of finite elements, and why really we want continuous arguments, why we want to enforce the solution at every point in the domain. Okay, this is what I wanted to talk about in this lecture, primarily interpolation and some motivation behind it. So in the next lecture, we'll look at the actual variational statement, and we'll formulate the equations. Okay, so thanks for paying attention, and I'll see you again.